Welcome to the introductory video about electrical potential. We're going to do something slightly different this time. I found a video that I really liked by a gentleman named Paul Hewitt, who is a physics teacher out in California, and he does a very good job explaining a lot of the concepts in this section. I will pause it every once in a while to mention some other things about the section, but in general we're going to follow along with his drawings and his thoughts on this section. It's chapter 25 in your book, and we'll start off by talking about electrical potential energy.
Let's talk about electric potential energy and its close cousin, electric potential. We'll begin with the more familiar gravitational potential energy. We know that a massive object raised in a gravitational field has potential energy.
Because of its location in the field, how far it is moved in that field.
When the massive object is released, say by the cutting of scissors, snap, its gravitational potential energy transforms to kinetic energy. Energy is conserved in the process. So it is with an electrically charged particle positioned in an electric field. When the particle is released in the electric field, snap! A lowering of its potential energy equals a gain in kinetic energy. Again, energy is conserved in the process.
I think it's interesting here, in the gravitational example, you've got mechanical energy conserved. You've got energy of motion, gravitational energy, going into kinetic energy. And you have, in this situation with the charges, you have electrical energy being therefore transferred into mechanical energy, energy of motion.
Recall in a study of mechanics that the amount of work done on an object can change the energy of that object. That's in accord with work, which equals the product of average force and the distance moved. Consider compressing a spring. The work we do increases the potential energy of the spring. Here's a positively charged metal sphere. And here's a small charged particle, say a positive test charge. In this position, relative to the charged sphere, the particle has potential energy. Now we push the particle closer to the charged sphere, and its potential energy is increased. What's happened? The work done, the average force times the distance moved, increases the potential energy of the particle. Got it? The particle has more potential energy closer to the sphere than it had farther away. Makes good sense.
This is another point I wanted to jump in. And if we look here at our electrical potential energy, there's a good chart down here down the bottom. Because when we're talking about mechanical motion, like the spring, we have only one direction of motion towards the equilibrium point. When we have charges, we have both positive and negative charges. Now, to do work to increase the amount of potential energy, if you have like charges, you have to do work to bring them together. This is what this little chart here shows. And if you have unlike charges, you have to do work to separate them. So you're always increasing the potential energy when you're moving the object from where it doesn't want to be. Just like rolling a ball up a hill. You're moving it away from the center of the earth, therefore you're increasing the gravitational potential energy by doing work. The difference with charges is sometimes they want to be together, like things do with gravity, when they're unlike charges, and sometimes they want to be as far apart as possible. That's with like charges. That's one of the big differences here with gravity as compared to electrostatic forces.
Now, if the charged particle is released, it will be repelled and fly away from the sphere. Potential energy transforms to kinetic energy. Let me ask you a question. In its flight, it passes its initial position. At that initial position, how will its gain in kinetic energy compare with its decrease in potential energy? That's right. Its gain in kinetic energy at this snapshot point will be equal to the amount its potential energy decreases. Again, conservation of energy rules. So far we've considered electric potential energy. Here's a charged sphere again, and we indicate its electric field. I want to lead you to a more important concept in electricity: electric potential. Again, consider a test charge in the field of the charged sphere. At any point, a greater quantity of charge means a greater amount of potential energy. But get this, not a greater amount of potential energy per charge. 2 times the charge gives 2 times the potential energy. 10 times the charge gives 10 times the potential energy. 2 divided by 2 is no different than 10 divided by 10. Whereas potential energy is measured in joules and charge is measured in coulombs, the ratio of potential energy per charge is measured in joules per coulomb. Our definition of electric potential is the ratio of potential energy per charge. We call the ratio joules per coulomb volts. Whereas potential energy is measured in joules, straightforward energy, electric potential is measured in volts.
One thing I wanted to mention here is while this charge, and no matter how big this charge is, when it's at that location, is at the same electrical potential, if we move that charge closer to the sphere, the electrical potential is going to increase because, again, we're increasing the electrical potential energy but not changing how much charge is there by moving it closer. So there are different levels of electrical potential. As we force charges to be where they don't want to be, we increase the electrical potential of each charge, increasing the amount of voltage, increasing the electrical potential.
1 volt equals 1 joule per 1 coulomb. A question: what's the value of voltage for a coulomb of charge with a potential energy of 12 joules? Did you say 12 volts? That would be nice. Then we see that 12 joules per coulomb equals 12 volts. And 50 joules per coulomb equals 50 volts, and so on. Let's continue. You'll seldom hear electrical types talking about electric potential energy. Instead, they talk about voltage, electric potential. If you rub a balloon on your hair, the balloon becomes negatively charged, like up to 5,000 volts, as shown here. That would release thousands of joules of energy if the charge were 1 coulomb. However, 1 coulomb is a very large amount of charge. The charge rubbed on hair is typically less than 1/millionth of a coulomb.
Remember that the charge on each electron, on each quanta, is very small. 1.602 times 10 to the minus 19th coulombs. That's a lot of electrons you can move, but still move a very minute part of charge.
Therefore, the amount of energy associated with the charged balloon is very small, even though the energy per coulomb, the voltage, is very high. A modest amount of energy divided by a tiny amount of charge produces a huge voltage. That's why being next to a 5,000 volt Van de Graaff generator isn't harmful, even when touching it. High voltage means high energy only if a great amount of charge is involved. More important are differences in electric potential, voltage differences, especially in electric circuits. Consider a common 12-volt automobile battery. Due to chemical reactions inside, a 12-volt potential difference is maintained between its 2 terminals. When a circuit is connected across the terminals, 12 joules of energy per coulomb pass through the circuit and through the battery. We've all seen birds perched on high-voltage wires. Why isn't this bird shocked? It would be if there were a voltage difference across its body. One foot may be at 1,000 volts, but if the other foot is also at 1,000 volts, no difference in volts means no shock. These ideas took me a long time to learn. I hope you learn them in a shorter time. Let's conclude with a question. Why is it a bad idea for our bird to reach over and make contact with another wire? What is likely different about the other wire? Until next time, good energy.
One aspect I wanted you to look at here is I have this little sim of a battery, and you have these blue charges bouncing around and these little rainbow colored stick figures, which actually represent a chemical reaction. If I have the battery here right now, it has 0 voltage across it. If I want it to have a large voltage, what the chemical reaction does is it does work on the charges, moving them from one side of the battery to the other. Now where the charges are concentrated here on the right hand side, that has a high potential because the charges don't want to be in there. It took work to put them together, so they have each one has a large amount of potential energy, thus a large amount of potential. On the other side, where there's very few charges that don't want to be near each other, you have a lower potential, and thus you have a potential difference across the battery, and that's energy that we can use for other purposes. If I go even further, then the charges get even more separated, more rarefied on the left, more concentrated on the right, and you get a higher electrical potential on the right and a lower on the left, therefore a higher potential difference. This would be your 9-volt battery as compared to your 1.5-volt AA battery, or something along those lines. The last topic that you're going to read about after class tonight is equipotential surfaces. We will look at these somewhat in the lab next week. You'll actually learn how to create these, and equi meaning equal and potential, so they're all at, each line on it is at an equal potential. Alright, so I hope you've enjoyed this video, and I will see you in class.